Hello everyone, my name is Saeid Ghasemalizadeh. I am PhD candidate at University of Calgary. Today I'm going to present my research on low Portland cement concrete mixtures made with ultrafine granulated blast furnace slag and a medium grade Metakaolin. So we did our research in the University of Calgary under supervision of Dr. Rahil Khoshnazar and my colleague Vaidehi Pitri from Department of Chemical Engineering is collaborating with us for the LCA results. As you know, replacing Portland cement with SCMs in concrete is still the most practical method for reducing the GHG emission of the concrete. And if we use the SCMs in an appropriate amount, we are improving the lattice strength and also the durability of the concrete. But when we are increasing the replacement level of Portland cement with SCMs beyond the currently used levels, so we will see a reduction in compressive strength, which is very significant at the early ages. And this is because of the dilution effect of Portland cement replacement. We have less PC in our concrete, which is reacting, and also it is because of the lower reactivity of SCMs compared to Portland cement. And a method to enhance the early age strength development of concrete with high SCM's content is to decreasing the particle size of SCMs through fine or ultra-fine grinding. And nowadays there are different types of mills that can reduce the particle size of any materials. And in literature we can see some examples of ultra-fine grinding applications for conventional SCMs such as fly ash and slag. So if we reducing their particle size, increasing their reactivity, they can contribute more effectively to the strength development of the mixtures. And it is also extended to mechanical activation of clays or naturally occurring silicate minerals, so they are making them reactive and they can be used as a new source of SCMs. And some industrial byproducts, non-hydraulic industrial byproducts, for example, such as steel slag. So if we do grinding and mechanical activation, so they are reactive and they can be used as SCMs. In this study, our focus is on ultra-fine granulated blast furnace slag, or UFS. And the objective of my study is to have a low Portland cement concrete using a combination of UFS and a medium grade locally available Metakaolin. So in this regard, first we prepare and did characterization on our UFS, and the UFS that we were aiming to achieve had a D50 of 1 micrometer, smaller than 1 micrometer. So then we test different combination of Metakaolin and ultrafine slag to replace 58% of cement in paste and mortar samples. And once we got the appropriate combination between MK and UFS, we scale it up to test in the concrete with our combinations. But in this presentation, I just focus on the characterization of UFS, and I will present the results of the concrete. The material, the cementitious materials that we used was commercially available cement, a slag, and a medium-grade Metakaolin. And for UFS, it was obtained from ultrafine grinding slag using a high-energy planetary ball mill in our laboratory. And for the case of concrete, we prepared conventional concrete, with a slump of 100 millimeters, and dry mix concrete. But we use locally available aggregates in Alberta. So for dry mix, we use aggregates from a concrete block manufacturing plants. And for the conventional mix, we use our aggregates in the lab. And for the conventional concrete, we aimed a slump of 100 millimeters. Cementitious material content was 390 kilogram per cubic meter, water cement ratio 0.39. And our concrete was air entrained with amount of 5 to 6% of the volume. And for our dry mix concrete, we use the cementitious materials of 380 kilogram per cubic meter. So we prepared each sample with different water to solid ratios to minimize the amount of entrapped air because it is dry mix, so we have a limited amount of paste. So we tested at different water to solid ratios to minimize the entrapped air. And again, because if this is a dry mix, so we prepared the sample by, they need compaction, so we use Proctor hammer to compact our samples. The binder composition that we use in our studies, so the reference sample was 100 cement, commercially available cement. So the first sample with Metakaolin and UFS, so from the total binder weight, UFS has 15 weight% and Metakaolin was 35. And we compared our results with the sample that has ordinary slag before grinding with the same amount of Metakaolin and Portland cement. So now I want to present the results for UFS characterization. So for the slag before grinding, the particle size was around 9 micrometer, 8.6, and it decreased to 0.9 micrometer. And for comparison, the mean particle size of Metakaolin and Portland cement was also about, was similar to the slag, about 9 micrometer. The second one is the crystalline structures of a slag before grinding and UFS after grinding. So here we saw a decrease in the intensity of some peaks, such as gypsum, calcite, ackermanite, and mervanite. So they were in the slag, but after ultrafine grinding, so they were amorphized. And the amorphous content of the UFS a little increased compared to a slag. The other characterization was the XPS, X-ray photoelectron spectroscopy, the binding energy of four main elements, calcium, aluminium, Si, and oxygen. And we saw a decrease in the binding energy of these elements after ultrafine grinding, which means that so they can be involved in the reactions more easily, so the rate of reactions will increase. And also, for the calcium peak, we saw a huge increase in the intensity of the calcium peak in UFS compared to a slag, which means that more calcium is now available on the surface of the UFS, so they can contribute in the reactions again faster and to a higher degree. We did the reactivity measurements on slag and UFS, so our UFS after grinding has a higher reactivity compared to a slag, and we did the test at 23 degrees. Now I want to present some SEM images from the paste that prepared with the Metakaolin and UFS. So in this SEM images, we saw almost two different microstructures, area A and area B. So the area A was a typical microstructure that we also saw in the sample with Metakaolin and slag before grinding. So some minerals in the clay, muscovite, or different morphology of CSH, so we saw in the area A. But the area B was mainly a CSH structure, very compact or homogeneous structure. So the area B is probably due to the reactions of the UFS, so it has calcium enrichment in the surface, so they can react faster and they have a separate microstructure. The compressive strength results of the concrete, so when we use only Metakaolin and slag before grinding, so we see a huge drop in the early edge strengths. But when we are using ultrafine slag and Metakaolin as early as 3 days, so our compressive strength is higher than the reference. And remember that we have 58% lower Portland cement. And the strength development continued at later ages and even at 91 days. And it was about 25% higher than the reference sample. The superplasticizer content comparison here you can see. So obviously when we are using ultrafine slag and Metakaolin, so we need superplasticizer content. But we can get a similar slump. So it was almost double the reference sample, but it was similar to the one with the slag and Metakaolin. Preliminary LCA results. So we first did the LCA results for Alberta, and the emission factor for electricity in Alberta is little high. So that's why. So our concrete with ultrafine slag and metakaolin doesn't show any decrease in GHG emission per cubic meter of the concrete. But if we normalize the results to the compressive strength, the GHG emission per cubic meter multiplied by MPa, so we almost see a comparable number between the slag and the sample with the UFS. But if we do grinding in other provinces which has a lower GHG emission per kilowatt hour of electricity, so we will see a decrease in the GHG emission of our concrete. And again, if we normalize it to the compressive strength, so the amount is much lower. This slide presents the results of our dry mix concrete. Again, at the 7-day and 28-day, our sample with ultrafine slag has higher compressive strength, but the increase is lower compared to conventional concrete at both 7 and 28 days. Yeah, for the conclusion, so we saw that ultrafine grinding of slag increased its surface area, decreased particle sizes, increased amorphous content, it decreased the binding energy of elements, so which resulted in a higher reactivity compared to ordinary slag. So in our concrete, we replaced 58% of Portland cement. We obtained a comparable early age strengths and higher late age strengths compared to sample with 100 commercial cement. And our LCA results show that the concrete with Metakaolin UFS could have a comparable or even lower GHG emission per unit strength compared to that made with slag and Metakaolin. So we have some research ongoing. The first one is to optimizing the particle size of SCMs in cementitious systems with respect to their chemical compositions. We are identifying the contribution factors to a strength enhancement of the systems with MK UFS through studying simplified models. We are assessing durability and shrinkage volume changes of the so-produced concretes. We want to include more performance parameters such as durability in our LCA analysis, and we want to scale up to produce high-strength concrete block masonry units with our dry mix. Thank you so much. I want to acknowledge the financial supports of NCERC, Canadian Concrete Masonry Producer Association, and Canadian Design Masonry Center, and our friends and staff at Innovative Concrete Technology Laboratory and University of Calgary. Thank you so much. I would be happy to hear your questions.